Qin Fang. Can you hear me?
Yes.
Hi, hello. Now we can begin now. So first, I will introduce you. Okay. Test it now. Okay. Hello everyone. Welcome to today's AsiaGraphics webinar session 24. I'm Shisheng Huang from Beijing Normal University. Today, we are very happy to invite two speakers. The first speaker is Professor John Matani from University of Tsukuba, Japan. And the second speaker is Dr. Qin Fang from University of Science and Technology of China. So let's welcome. Okay. So today's first talk is curved origami design. The speaker is Professor John Matani. Matani is a professor of information and system at the University of Tsukuba. He received his PhD in engineering from the University of Tokyo in 2004. He has been present post since April 2015. His research interests center on computer graphics, in particular geometric modeling techniques, and their application to origami design. The origami artworks created by him have features that are three-dimensional shapes with smooth curved surface. His main books are 3D origami art and curved origami design. In 2010, through an exchange with Issey Miyake, he contributed to the launch of the new 132.5 fashion brand. He also cooperated in the design of origami used in the movies Shy Godzilla and Death Note Light Up to the New World. His unique origami has been well received around the world, and he has received invitations to hold workshops and exhibitions in Germany, Switzerland, Italy, Israel, and many other countries. His work has inspired the design of the trophy for the player of the match winner of each game at the Rugby World Cup 2019. His major awards are Microsoft Research Japan Informatics Research Award and the second Japan Society for Graphic Science Award. He was appointed as a Japan Cultural Envoy from the Agency for Cultural Affairs in 2019. He visited 8 Asian countries in November and December 2019 as the envoy. So, Professor John, are you ready? You can begin now. Professor?
Yes. Oh, sorry.
Okay.
Thank you very much for the introduction.
So you can open the screen test.
Okay.
And share.
Yeah. Okay. So thank you very much for the introduction. And my name is Jim Itani, and I'm from the University of Tsukuba in Japan. Today, I will talk about the curved origami design as shown in this top page slide. I am interested in designing this kind of curved origami. And although the chair introduced me, I will also give the short self-introduction. And I am at the Department of Computer Science, University of Tsukuba, and my research area is computer graphics and geometric modeling, and especially focusing on origami design. And I also active as an artist, so I created many origami artworks as shown in this page. And I posted several origami artworks of my design on Instagram or Flickr, other photo sharing services. So if you have interest in my origami pieces, please access to the web page after this session. And I have published 2 origami-related design books in English. One is carved folding origami design, and the other one is 3D origami art. And they are mainly focusing on the techniques, how to design the carved origami models. On today's talk, I will provide topics related to shape modeling of origami, that is the shapes that can be made by folding a single sheet of paper. And the main focus is on introducing the origami design applications that we have developed over the past 10 years or so. And so the topic is rather old-fashioned, classic mesh-based shape modeling techniques. So unfortunately, it is not a state-of-the-art shape modeling technology based on recent modern machine learning. But it is not novel, but I hope you will be interested in it because it provides a topic that specializes in a specific category of origami. And as you may know, the modern machine learning technique is red ocean, but the origami is very blue ocean. So I think it is not so difficult to catch up the top of the origami design of research. Okay, so I will first briefly introduce some origami pieces I created recently. So now I think you can understand what kind of the origami I am interested in. As this photo and the CG rendered image show, the curves are included in the 3-dimensional shape. And mainly I am interested in making this kind of the smooth surfaces with curved folds. And this is a origami model. I put it on the top page of the slide. I prefer this cute origami pieces. And recently I designed this kind of the object, and these are made from a single sheet of paper. And these are also with the same kind of origami. Okay, so first, I will briefly introduce the geometry of curved folds because this is already clarified in the area of differential geometry. So the mathematical basis is clear. So the problem to design the curved origami is not for in the field of mathematics, but for the area of the user interface of or the handling on the computer graphics. So the basic knowledge I will introduce is related to the 3D shape and the map to the patterns. These are very basic equations, but I will introduce one by one because it's very important to understand the relationships between the 2D pattern and the folded 3D shapes. The kappa 2D is a curvature of the 2D crease lines shown in blue here. Equal the curvature of the curve in folded state in 3D space, shown in red curve here. Multi times cosine alpha s. Alpha is a folding angle shown in blue lines here. So this is a relationship between the curvature in 2D and the 3D. And the cotangent beta L and cotangent beta R represent the angles between the rulings and the tangent vector on 2D plane. And these angles have these relationships. That means the angle beta and left side and the right side are decided by the curvature of the 3D curve and the folding angle. And also it contains the value of the torsion. So with these equations, we can reproduce the 3D shape from the 2D pattern and the 3D curve that represents the crease. So these colors expresses the elements used in these equations. The red one is 3D crease curve, and which is defined by curvature and torsion. And blue one is the 2D crease curve, which is defined by curvature in 2D. And finally, the blue one is the fold angle, which is not constant, which may differ by the positions. And with these equations, we can make the 3D shape and the 2D pattern at the same time from the two of above parameters, A, B, and C, which means two of three are clear. We can make the another one parameters. So we can reproduce the 3D shape from two parameters in three. Okay. So as I said, the mathematics of curved fold is revealed. So but we still do not know how to design attractive curved origami. So today's topics I will talk is in three. And one is 3D design approaches. And the next one is curved folds on origami simulator. And finally, I will talk about the design interface for space curved folds. At the beginning, I will talk about the properties of developable surfaces. Developable surfaces is considered as a surfaces consisted with line elements. As you can see in this page, the conical surface or cylindrical one and the tangent developable are well-known three classes of developable surfaces. The conical one consists with lines that cross at a point. We call this point as apex. And the cylindrical surface consists with line elements that are all parallel, like this. And tangent developable is consisting with line elements that are a set of tangents of a space curve, like this. And all of these surfaces have the properties that the Gaussian curvature at any point is all times 0. So there exists an isometric map to a plane. So which means these surfaces can be made with a single sheet of paper or without any distortion. So now we can say that we can make a cone or a cylinder from a single sheet of paper like this. But unfortunately, we cannot make a sphere because the surface of a sphere has a non-zero Gaussian curvature. So we can say that it's impossible to create a sphere. But I had a question. Is it really impossible or not? Because we can observe that the candies are spheres wrapped by a square sheet. We can see this kind of wrapped candy in the store. So we can observe that the sheet without any distortion and no gaps or no cut, we can make a sphere, wrapping a sphere. The reason why we can make a sphere from a single sheet of paper is that the paper has small wrinkles. That means as tiny folds. I can say that adding folds on the paper is a kind of technique of origami. So we can make a sphere adding folds. Based on this simple concept, we can make the 3D model by applying the folds on the surface. As this animation shows, starting from the wrapping sphere, we can unfold into a flattened state. As you can see, by adding the folds in symmetrically, we can calculate the exact flaps or folds on the paper, and we can simulate the wrapping sphere by a single sheet. And there are another way to wrap a sphere because the left side is a wrapping sphere with a single twisting here. And in this case, we can see that twists in both bottom and the top in 2 positions. So we can make the 3D CG model by calculating the location of the flaps as same as the first case. So we can observe the animation of the model, always this surface area keeping in the same. And there are no distortions. Okay, so I will introduce a very basic idea of how to make the previous animation. We will start the intended 3D model, and then we can make the maps by unfolding, by cutting along the edges. But cutting is not allowed on origami, so we have to fill the gaps to make the pattern on the 2D. And then we can modify the gap and locate and add to the original 3D model to make it consistent with the flattened pattern. There are several possibilities to achieve this, but I took the approach for adding flaps or adding protrusions around the surface. By doing this, we can now make the pattern of the sphere like this. By starting from the divided surface of the sphere, we can make the pattern as shown here. The yellow area represents the surface of the original sphere, and the green area shows the gap we have to fill out. And then the gap is located to the outside of the sphere surface. And we can make these origami models from this pattern. And another possibility is shown here. We can make this pattern also from the same sphere. And again, the green area is a gap. And we can make this model by folding and making the gaps outside of the sphere. By applying this basic idea, now we can implement this idea on the designing system. So I will show the demo of these applications. Okay, just a moment, I will switch the screen to the application. Okay, this is a very simple application developed on the web application. And this is written on JavaScript with JavaScript. So here I will show a very quick demo. We can input the polyline in the screen, and this black line represents our axis for rotational symmetry. So then the 3D model is generated in right top side, and this is real time. We can change the location of the position of the vertices, and the unique point is that the vertex can move across the rotational axis. By doing this, the 3D shape has this twisting path like this. And by looking at the bottom, we can see a small hole exists. So now we can close this hole by moving the vertices like this. And now you can see that the crease pattern is automatically generated from this 3D model. And there are several parameters to change the shapes. And of course, we can make the smooth curves by dividing the input polylines into subdivided polylines like this. So now we can see the curved surfaces model like this. And there are some examples already I entered. For example, this is a sphere model and the eggs and twist tower like this. And you can see that the input is very, very simple. So you can try on the web page by Google the Olivevo, the name of this software. Okay, so I will go back to the presentation slide. Okay, by using this application, now we can make many origami shapes as we like. So the final process is making origami foldings by human's hand. It is very difficult part, but I am used to. So I can create a very nice looking, attractive curved origami models. I will show a short video which show the making process. This is 4 times faster than real time. So this video is 1 minute. So actually I created this origami pieces in 4 or 5 minutes. Starting from the regular hexagon, I added curved folds. As you can see, the flat sheet of paper changes the shape slightly, and a small folds are added like this. Because it is very difficult to add smooth curved folds without any scores, so I added creases beforehand by using the cutting machine. Okay, now it's almost finished. You can see that the final shape is so quickly created like this. Okay, so this is a video of the cutting plotter. I plotted the crease lines on the paper by using this kind of cutting plotter. Okay, so I have many origami pieces in my laboratory, and I displayed some origami pieces in the department store. Okay, so now I move on to the next topics of interactive design of frontal curved folding by using the reflection. This is a very old research topics, but I think this is important to create origami models with interactive interface. This is very basic theory. Fold can be added to a developable surface by reflecting a part of the surface by an intersecting plane, as this figure shows, by adding a plane and then reflecting a part of the original surface. We can get the developable surface with creases. And this is developable, so we can make the right side shapes as a single sheet of paper. And by applying a set of mirror operations, we can make rather complicated shapes from a single simple shape. So by applying the mirror reflections, we can make this kind of origami models from a single cone. And by doing this, we can make this model from a single sheet. This is a map of the model, so we can reproduce the geometry from a single sheet of paper. And I will also show the very quick demo of this software. Okay. Okay, so this is the application. So now I pick the vertex of the model. And then we can drag the position of the vertex as we like this, and then fix the shape. And again, we can pick and move the position. I picked wrong point. Okay. Like this. And we can repeat the same operations like this, and then we can pick any vertex as we like. So we can change the shape like this. Okay. So this is very simple, but the idea is very important to realize interactive editing. We start from a single developable surface and click the vertex and then drag the vertex. And how to realize this? The idea is shown in this slide. When the user drags the vertex of the surface, the system automatically calculates the mirror plane from the starting point of the vertex and the current position of the vertex. And by dividing this line segment into two, we can define the intersection of the plane. And the model is updated by reflecting the dragging part like this. So the idea is very simple, but by using this software, now we can create many different type of origami models as shown here. So these models are designed by using the software. Okay, and there are several models like this. And left side is the initial developable surface, and the second one is a model we design and Chris pattern and the photo of the model. Okay, and next is another user interface for designing column-shaped origami based on mirror reflections. The idea is almost same with the previous one because the model is generated by applying the mirror operations. Before talking about detail of the algorithm, I will show the application. And the application is divided in several windows. I will share the screen. Okay. Okay, there are 4 screens here. And now we can input the polylines and almost same with the first application I introduced you. But the difference is that we can also design the top view of the model. So we now input the cross section here, and then we can also input the top view of the 3D origami models. So by inputting the zigzag pattern as a cross section and the zigzag pattern on the top section, we can get this 3D model under the constraint. So now we can interactively change the position of the vertex, and also we can change the shape of the top view model. And by using these interfaces, we can now design several different origami models from this. Okay. So now what I input is the profile polyline shown here. The system sweeps the profile polyline, and then we also define the trajectory path. By inputting the profile polyline and trajectory path, we can make the 3D origami shapes, as I showed before. The basic concept is reflection. So from the trajectory path, the system automatically calculates the location and the orientation of the reflection plane. So the user do not need to care for that. By inputting two polylines, the 3D shape is very easily designed. So this is an example. If we input the profile line like this, and also we input the trajectory path like this, and then we obtain this kind of origami models. Okay. So there are another case, this zigzag pattern generate the Miura patterns. And also this simple input creates a well-known Yoshimura pattern. So this interface is very powerful, which can design already known patterns with simple interface. Okay. And this is some result. We can get this software. These photos I created. Okay, so now I will move on to the curved folds on Origami Simulator, which is published in the 2021. And I think some of you may know the Origami Simulator, which runs on the web browser and which simulates the folding motions on the crease patterns. So, but then the previous origami simulator that cannot handle the curve. So originally, the origami simulator makes the triangle mesh from the input curve, but it is not suitable for simulating the curved folds. So we try to improve this feature by improving the meshing algorithms, which is named by as ruling-aware triangulation, which means that triangulation is very important to define the final shape. Because the curved surface are consistent with the ruling lines, we have to take care for the straight lines on the surface, and they should be included in the triangular mesh. So this shows the initial origami simulator, and this is a result we implemented. Okay, so this is a very, very simple algorithm and outline of the proposed method. We start with the crease pattern having the curves, and then we discretize them and employ the constrained Ronne triangulations. And this is not good for curved origami simulation. So we apply the edge swap operations to improve the triangle mesh. So the basic idea is to make the rulings almost perpendicular to the crease lines. So we define the error functions as shown here, which calculate the difference between the perpendicular angles and the original angles. So to minimize the error, we iterate the edge swap operations. So starting from the crease pattern, and we can make the final mesh like this. And this is a result. We can now simulate the curved folds as these figures show. Just inputting these crease lines, we can get the 3D shape. And it is very similar with the actual origami models made with a physical paper. And this works very well, even the crease pattern is complicated. So this is the crease pattern we design, and the final model is almost similar with the actual origami models. Okay, so starting from the curved lines, we can make the 3D model like this. So this feature is now implemented on the origami simulator. So now you can simulate the foldings with creases like this. Okay, so this is the last topic I have prepared for this session. And the final one is the interactive curved fold modeling using a handle curve. And this is the latest study of our laboratory. And this is published in this paper. And the goal is to design this kind of the curved origami models interactively because this shape is easy to create a paper, but it is not easy designing on a CAD or CG systems because the fold curve has a space curve and crease pattern and rulings have to define very precisely. So the target shape is as described here, which is developable surface and with a single curved folds. Okay, so this is the origami models made with these simple crease patterns. And this video shows how to create these origami models. Even though this process is very easy, but it is very difficult problem. How can we create this 3D model on CAD CG software? This showed the creases on the space. So we propose a method which accept as input. First one is crease curve, and the second one is handle curve, a copy of the crease curve. So by using this handle curve, we can define not only the crease curve, but also the shape of the developable surfaces. So by using these two curves, we can define the final shape. Because due to the time limitation, I will skip the detail of the algorithm, but I will briefly just explain the just concept. So the crease curve is designed, input by the user, and the handle curve is generated by the system, and the user control the shape and the location of the handle curve. And then the system automatically generates the developable surfaces consistent with the rulings that are generated between two curves. And I will show the interface of the proposed system. And the black curves are creases, and then this yellow curve is a handle curve, and the user can move and change the location and the shape of the handle curve, and the system automatically update the developable surfaces. It looks like very simple, but system have to calculate the mathematically correct shapes, not only considering the location of the handle curve. The system calculate the exact shapes according to the formulas I initially introduced in this talk. By applying this approach, now we can design this kind of origami shapes just by inputting two curves here, black curves and green curves. So black curve represents the creases, and this green curve define the body of the developable surface. and the reflected folded thus developable is automatically calculated. So we can get this shape. And this is the way to design these origami pieces. And the system generated by changing the shape of the handle curve. And you can see that this graph represents the relationships of the folding angle against the parameter or arc length parameter of the crease curve. So we can see that the angle changes in very unusual curve. It's not easy to predict these relationships. So it's possible if we can enter this curve manually to design this model, but it's very difficult problem. However, by using our interface, the user can easily design this model and the angle is automatically decided. And this shows the maps of the 3D surface. Okay, so now we can create this kind of one curve fold origami shapes very quickly. Okay, I think now is the time to wrap up my talk. And here is a summary. And the geometry of curve folding has become quite clear in mathematics. But our user interface is crucial for designing artistic shapes. So we developed several design tools for curved folds and created various shapes. And I will show some future work. And many artworks are made by the minute expansion and contraction at the folds to achieve expressive shapes. And a shape modeling tool that allows for minute distortion in folds is desirable, but we don't have such a tool. So this is a kind of future work to make this tool. And research and development using heat deformating materials that take into account manufacturing processes such as self-folding is a very hot topic these days. So this could be one direction we have to consider. Okay, so this is the end of my talk. Thank you very much.
Okay, thank you, Professor Matani. Thank you for your wonderful talk with many nice origami results. Thank you. So let's see questions. Okay. Oh. Okay. Professor Martini, we have two questions. And the first question is, can you how can you think the problem to automatically created the curved folding for any given 3D models? So how do you think how can we solve this problem if we if we would like to automatically created a curved folding for a given 3D models?
Yeah, thank you very much. I understand the question,
Yes.
but
Yes.
it is a very difficult problem, I think.
Yeah. Okay.
Yeah, even for the origami artist, that is very challenging, and there are no solid solutions. We don't
Okay.
know how to realize any 3D shape.
Okay.
As you may know, the Professor Tomohiro Tachi achieved that by adding the tags on the surface. So the surface could be discretized as a triangle mesh. It could be possible, but the curved folds is another difficulty. So I don't know how to realize that could be the future work or new research topics.
Okay, thank you. So the second question is, how can you think the machine learning methods can be used for the origami design? What do you think?
I'm sorry, I cannot follow the first sentence. Can you repeat it again?
Okay, so the question is, how do you think the machine learning
Machine learning.
methods, yes, can be used for the origami design? How do you think this are?
Yes. Machine learning is very popular, and machine learning is employed in many fields, including the computer graphics. But unfortunately or fortunately, the machine learning is not employed on origami design, so it is empty. So now anyone can try to use machine learning. It could be the novel approach. And I don't know how to apply the machine learning for origami design, but I hope if I could. Thank you.
Okay. Thank you. Okay, so that was the question. So let's thank Professor Matani again. Thank you.
Hi, thank you very much. Bye-bye.
Okay, bye-bye. So, uh, so let's begin the second talk. The title is From 3D Models to Paper Graft, the process of developability. The speaker is Dr. Qin Fang. Dr. Qin Fang is the postdoctoral researcher in the School of Mathematical Science, University of Science and Technology of China. He received his PhD in 2021 from University of Science and Technology of China. His research interests include geometric processing and computational fabrication. So, Dr. Qin Fang, are you ready?
Oh, okay. Thanks
Okay.
for the introduction.
Okay.
I first.
Okay, you can begin now.
I'm to share the. I. Sorry. Wait a minute. Sorry, can you hear me?
Yes.
Sorry, I have assigned the. Okay, sorry. Okay, thanks for the introduction. I'm glad to share our work on algorithms for converting 3D models to papercraft. Papercraft involves creating 2D or 3D shapes using sheets of paper that are cut out, folded, scored, and glued together. There are various types of papercraft, which use different combinations of these operations. When discussing 3D papercraft without specified types, it generally refers to paper model, which involves all three operations. Okay, here we show a simple example of a paper model. First, the penguin pattern needs to be cut out, then folded in 3D so that the parts marked with the same letters overlap. And finally, we can glue them together. We can easily find some software which turn a 3D model into 2D papercraft template. They take a simplified mesh as input and unfold it into separate pieces. These pieces are usually narrow and broken, placing a heavy burden on fabrication. This software do not consider the curved shape form by bending paper sheets, which are developable surfaces. There are three types of developable surfaces: cylindrical, and conical, and tangent surface. The improvement is significant when curved shapes are allowed in papercraft design. The output model is more faithful with larger and fewer patches in the 2D templates. Thus, papercraft design can be approached by generating piecewise developable patches. Once we have piecewise developable patches, each patch can be flattened into 2D charts and then glued together based on the boundary correspondence between the patches. The question is how to generate a piecewise developer for approximation. Since most models are not globally developable, we first need to segment them into patches and then approximate each patch with a developable surface. To achieve high fidelity, it is important to control the approximation errors. This can be done by ensuring that each patch is not too far from being developable. During the segmentation stage, a proxy that evaluates patch's developability should be considered. There are various segmentation methods proposed for generating piecewise developable approximations. Explicit developer proxies such as strips, cones, or wrapping by papers can be used. Since the strategy is heuristic and the segmentation relies on the fitting of an explicit proxy, the resulting approximation error tends to be large. In contrast to explicit proxies for segmentation, implicit developable proxies are used to deform meshes, making them nearly developable on most areas. This approach yields a more faithful output mesh, but there is a low explicit patch layouts, and the non-developable areas on some unclosed seam curves. Okay, next I will share our three work on the piecewise developable approximations. During the segmentation stage, different developable proxies and algorithms for these proxies are designed. Let's introduce the first work, developability-driven piecewise approximations for triangular meshes. Although methods use implicit proxies have low explicit patch layouts, The same curves on the deformed mesh make the segmentation stage simple and reliable. Based on this fact, our algorithm and deformation stage before segmentation stage and perform segmentations on the deformed near the developable mesh. Then approximation can be achieved by refining the segment mesh to reduce the discrete Gaussian curvature while keeping the patch smooth and the approximation error small. In deformation stage, energies include the implicit developable proxy and approximation errors and mapping distortion. We minimize it to obtain a nearly developable mesh. Central to the deformation process is an implicit proxy using new edge-oriented notion of discrete developability. Under the Gauss map, a developable surface degenerates to a set of curves. And this degeneracy condition can be moved from continuous Gauss map to the discrete normals. Instead of applying this condition to the triangle normals, we force the condition on the edge normals to define the discrete developability. For each edge, the edge-oriented discrete developability requires the 5 edge normals of it, and its neighbors satisfy the 4 determinate conditions. Due to the relationship between the edge normals and the triangle normals, our edge-oriented developability is still affected by the mesh connectivity. Here we show the examples of the cylinder. However, our developability definition is weaker than the definition in Stan et al. 2018. And the deformed mesh driven by our developability entity is more faithful to the input shapes. The determinate condition is highly nonlinear and hard to minimize. To overcome this challenge, we introduce auxiliary variables to decouple the nonlinearity. Here, PR represents the closest projection of a 3x3 matrix into a rank 2 matrix space. Then the implicit developable proxy can be defined through the distance from the normal matrix to the projection. PV is the closest projection of a vertex position to the input mesh. And then the approximation terms is the sum of square distance from the vertices to the input mesh. We use each face normal to decouple the nonlinearity between the vertex positions and the edge normals. The edge and the face normal are transformed by 2 types of rotation matrix when deforming mesh. The matrix U represents the rotation of triangle normals with respect to the bisector. And the matrix R is used to encode the overall rotation of edge normal and its one ring. Then, edge and face normals satisfy the following equations. The distortion terms are added to keep the relationships between auxiliary variables and the vertex positions. Here, the scaling S is of each edge is the ratio of length. To optimize this problem with these 7 types of variables, we use the block nonlinear Gauss set method. Each type of variable form a block, and we optimize the variables block by block. Our segmentation strategy contains two phases: a coarse partition process that produces an over segmentation based on the normal difference between adjacent triangles, and a patch merge stage that reduces the number of patches onto the discrete Gauss curvature. The first step is the over segmentation process. For one patch, we define the developability metric for the segmentation algorithm. If its metric is larger than a positive threshold, we use the elegant spectral mesh segmentation algorithm in Tong et al. 2020 to segment this patch. Then we perform the segmentation for patches in descending order based on the developability matrix. The second step is patch merging. We first find the unvisited patch with a minimum area and the set of its neighbor patches as merging candidates. For each adjacent patch, if the boundary length is smaller than a threshold, or if there is a vertex with a high curvature on this boundary, we remove this adjacent patch from the candidates. Then we choose the candidate that generates the most straight boundary after merging, and merge it with the P-mine. This step-by-step merging process generates final patches with a larger area and smooth boundaries. We use the refinement similar to Ion et al. 2020, which defines proxy by wrapping paper. There are two differences. First, our approximation term measures the distance from vertices to the deformed mesh, instead of the distance from vertices to the wrapper. Second, we do not cut the seams and split vertices on seams. It avoids the gaps between adjacent patches that appear in the results of Ion et al. 2020. We test our algorithm on models with different destinations and noises. The host-off distance between the input shapes and all our deformed results are small, and the segmented patches are smooth and discrete developable. The larger noises cause the patch boundaries to become more highly curved. But we find in practice, the noise does not lead to a large increase in the number of patches due to our coarse-to-fine segmentation strategy. Besides, we test the deformation process on several developable or nearly developable models. Our algorithm generates faithful results. Here are some approximation results generated by our algorithm. To compare with Stan et al. 2018 and Binninger et al. 2021, we first use their methods to deform the input mesh, and then apply our segmentation and refinement to generate the piecewise developable approximation. For deformed meshes, they generate larger approximation errors, and their seam curves seem to be less salient. For piecewise developable approximations, they generate more patches, and their two-sided cost of distance are 2 to 4 times greater than ours. We also compare with Ian et al. 2020, use the models provided by the authors. Their approximation error is larger, and the more patches are required than ours. Here we fabricated 70 models using paper sheets. We print it into the paper sheets and cut it out and glue them together. This is the bunny model, which is made by piecewise developable patches. Here we show another 4 models. Our first work present a novel algorithm, combine implicit developable proxies and explicit segmentation strategies. The implicit developable proxy is defined as a new edge-oriented notion of discrete developability, which is further optimized by block nonlinear Gaussian-Seidel method. Due to the edge-oriented developability still depends on mesh connectivity. The second work defines the developable proxy through the Gaussian curvature of the signed distance field. The key idea is to use implicit representation to be indeterminate of testimation. We use the signed distance field to represent the deformed results. The deformation is to update the parameters of the neural network by optimizing a loss function containing the implicit developability proxy. Then the updated SDF is extracted as a triangular mesh, and we cut it into disk topology along the features. Finally, an iterative algorithm is proposed to improve developability. The positions and the number of extra cards are optimized to remove punch overlap. There are 3 loss function terms in neural deformation stage. Due to the Hessian determinant of signed distance field is the Gaussian curvature on implicit surfaces, the proxy of developability can be defined as the projection of Hessian matrix to the rank 2 matrix space. The second term is the approximation error, and the third term maintains the deformed implicit field as the SDF. When getting the deformed results, we transform the implicit field to a triangular mesh and find a feature point for each high curvature region. Then we generate the initial cut by constructing a minimum spanning tree that connects all feature points. After obtaining the initial cut mesh, we propose an iterative partition method to generate the dissolved piecewise developable approximation. The iterative method contains 3 steps: a discrete developability optimization step to reduce the Gaussian curvature to approach 0, and the future guided removal stage for fabrication, and a length-aware patch merging phase to reduce the number of patches. These 3 steps are repeated until there is no self-intersection on flatted patches. Our method successfully generates high-quality piecewise developable approximations. Here we show some examples. We perform the comparisons with 2 automatic methods. As shown, all our results have fewer patches and smaller approximation errors. Here we show 6 models made from paper sheets. In conclusion, the second work proposes a novel and automatic method to compute a piecewise developable approximation from the input shape. The implicit neural shape representation makes the deformation independent of the tesselation. And we develop an iterative optimization process to enforce the developability and remove the overlap for each patch. Let's introduce the third work. As mentioned above, apart from the approximation errors and the small patch numbers, the piecewise developable approximations also require a short patch boundary length and penalties for small patches and narrow regions. However, these continuous or discrete variable requirements affect each other, which makes it difficult for optimization. The genetic algorithm is an optimization method similar to the process of population evolved in biology. First, it obtains an initial population of a series of individuals through a specific method, and then finds a balance among various measures by defining a special fitness function. Through the evolution of the initial population and the genetic operations, the complex function is optimized. Therefore, our main idea is to optimize the problem with a complex objectivity and constraints through a genetic algorithm. In our genetic algorithm, a chromosome is a partition. For chromosome, our fitness function includes those 4 quality metrics: approximation error, and patch number, patch boundary, and topology term. However, evaluating the approximation error for the fitness function is non-trivial. The proxy mentioned in the first two work requires deforming mesh to be nearly developable, which are difficult and time-consuming. Resolving the challenge is based on the key observation, the approximation error and the mapping distortion between the input surface and its developable approximation are positively created generally. Then we define a proxy using the mapping distortion. Here we use the area distortion of a conformal mapping, which can be calculated quickly. The genetic algorithm starts from an initial population consisting of many chromosomes. Then it performs genetic operations, including selection, crossover, and mutation to evolve the population to find a chromosome with a small fitness value until the termination conditions are satisfied. Initial chromosomes are oval partitions, which can be computed by the VSM segmentation method. We adjust the consanguinities and seed number in the VSA to initialize the various chromosomes. In selection operations, the init selection makes excellent chromosomes converge quickly. Therefore, our selection operation uses the fitness value and the generation relations to output the new chromosomes and select only one among each parent and its children. The crossover operation receives two different chromosomes as inputs and outputs a new chromosome. For partitions, it replaces a part of the patch boundary of one chromosome with the part of patch boundaries of another chromosome. In mutation operation, we develop 5 types of operations for different goals, including the merging patch operation, removing small patch operation, and the shorten boundary operation, removing narrow region operation, and the smoothing trapezoid boundary operation. After obtaining the output partition of a genetic algorithm, we perform an approximation stage using the method in our first work. Our algorithm is tested on the Velas model with different triangulations. We obtain a small approximation patch error and a few patches for the meshes with the non-uniform and isotropic tessellations. We also obtain a reasonable result for the noisy input. We first test our method on various models, including CAD and organic models. Here are some examples. Besides, we run our algorithm on several developable or nearly developable models. Our algorithm generates the reasonable results for the left 3 developable models. For a nearly developable model, we generate 3 patches with low approximation errors. We compare with the Ian et al. 2020 and our first work. Except for very few results, our results have smaller approximation errors. and a smaller number of patches and a shorter boundary length than the competitors. We fabricate another 6 models using paper sheets. Our third work presents a novel algorithm to compute a piecewise developable approximation for triangular meshes. We use a generative algorithm to optimize the complex objectives and to efficiently evaluate the approximation error in the fitness function. We creatively use the conformal mapping techniques, which can compute fast. In our 3 work, different proxies of developability are proposed. Our edge-oriented developability depends on mesh-driven connectivities, and the block nonlinear Gauss-set method takes more than 1 hour on average to converge. And in the second work, we use the Gaussian curvature of a assigned distance field, but the training and the deformation part of SDF takes most of our method time. It is worthwhile to accelerate the training process and reduce the memory costs. Although computing area distortion of conformal mapping is fast, the evolution of genetic algorithm takes several minutes. Thus, it is necessary to figure out what kind of developability proxy is suitable for segmentation to build an efficient algorithm. In the segmentation stage, other requirements may need to be met, such as the human intuition or global smooth and global constraints. Thank you for your listening.
Okay, thank you, Qingfang. Thank you very much for your nice talk. Okay, so let's look. Do we have any questions? Okay. We have 2 small questions. So the first question is, you have mentioned that your approach is very time consuming due to the high computational cost. So do you think what's the most effective way to make your approach more efficient? So
yes, yes, that's a good question. As we show, there are we use the different the proxy of developability, but all of them are time consuming. There are efficient way to measure the developability on the mesh. And we need to design a proxy which is suitable for the segmentation. This is where we want to do. If we only to design use the like a Gaussian curvature, they kind to form a good segmentation. So how to design a suitable proxy of developability is still remain challenging, and I haven't think a good method to do this effectively. Yeah, it's an open study and have them fixed answer.
Okay, Okay, thank you. So the second question is about the segmentation. So how is the different kind of segmentation influence the final results of the final results of your approach?
Yes, as we mentioned above, in our fabrication, first the patch number need to be small. So there be fewer patches. Next, we do not want to the patches to be narrow. It means we need to cut out along a long boundary. This is time consuming. And other requirements we have never to, we haven't to consider, such as the feature, how to keep the feature, or the global smooth, global constraints how to add. We haven't to add to them to our algorithm because it is difficult to define it. Thus, for fabrication, the criteria I mentioned above is I think is already them.
Okay, thank you. Thanks, Qinfang again.
Okay, thank you.
Okay, so that's all. Let's thank Professor Matani and Dr. Qinfang again. Thank you. So today's webinar is now. Thank you.
So thank you very much. I will be out. Goodbye.
Goodbye. Bye bye.
Bye.
Bye bye, Professor.